All right, let's dive right in. Welcome to this explainer on support vector machines, or SVMs. Today, we're going to explore what is honestly one of the most beautiful geometric ideas in all of machine learning. Now, if you've been following our previous analyses on gradient boosting algorithms, things like XGBoost or LightGBM, you're probably used to models that build hundreds of decision trees just to inch closer to the right answer. But what if I told you we don't actually need a single tree? Instead, we're going to use pure geometry to find the absolute perfect boundary.
Take a second to think about this quote. It perfectly captures the core philosophy of a support vector machine. You know, in machine learning, we get so caught up in just minimizing mistakes, but SVM, it thinks totally differently. It prioritizes space, clarity, and maximum separation over simply correcting errors. It really is a completely different way of looking at how we categorize our data.
So, here's our roadmap for today's explainer. We'll start with Part 1, the perfect decision boundary. Then Part 2, meet the support vectors. Part 3, handling messy data. Part 4, the famous kernel trick. And finally, Part 5, SVM in practice. Okay, Section 1, the perfect decision boundary. To really wrap our heads around SVM, we need to compare it to how other algorithms learn. Imagine two teachers grading exams. Gradient boosting is kind of like a teacher who obsessively studies every single mistake a student makes, constantly tweaking and correcting their grading system based on those errors. SVM, on the other hand, is like a teacher who just takes a step back and asks, hey, can I just draw one fair, perfect line that separates the passing students from the failing students? It focuses purely on finding that single, optimal boundary from the get-go.
But here's the catch. If you plot a bunch of data on a graph, you could probably draw dozens, maybe even hundreds of different lines that technically separate Group A from Group B. So, which one is the safest? Well, think about building a highway through a valley between two steep mountains. The safest road isn't built right on the edge of the left cliff, right? And it's definitely not right next to the right cliff either. The absolute safest road is built right down the middle, where you have the maximum amount of breathing room on both sides.
That empty breathing room? In SVM, we call that the margin. The margin is literally just the distance between your decision boundary and the nearest data points from each class. Think of it like separating two rival football teams. You wouldn't put them 1 meter apart, you'd put them 20 meters apart to avoid a brawl. SVM always prefers the widest possible separation. Why? Because the wider the margin, the safer and more robust our model is when new, unseen data comes rolling in.
Which brings us to Section 2, meet the support vectors.
Now that we know we want the widest possible margin, how do we actually calculate that exact line? Let's say you have a dataset with thousands of points. You'd naturally assume every single point matters for calculating the line, right? Actually, no. Think about parking a car between two brick walls. You aren't looking at every single brick in the entire wall. You literally only care about the few bricks that are closest to your bumper. In SVM, the vast majority of your observations don't influence the boundary at all.
And this perfectly illustrates what we call support vectors. They are that handful of critical observations sitting right there on the edge of the margin. It's like a massive game of tug of war, where only the players closest to the center line actually determine the balance of the rope. These specific data points literally support the entire model, just like the main pillars of a bridge. If you move a point that's far away, absolutely nothing happens. But if you move a support vector, the whole boundary shifts.
Moving on to Section 3, handling messy data. Obviously, we don't live in a perfect, clean, geometrical universe. What happens when perfect separation is just impossible? Say you have a single wonky blood glucose measurement that falls on the totally wrong side of our graph. Or maybe a kid accidentally leaves their toy in the neighbor's yard. If you force the algorithm to make a perfect boundary, it would have to draw this crazy, distorted, zigzagging fence just to account for one tiny anomaly. Forcing a perfect split like that would completely ruin the general rule for everyone else. This brings us to a huge concept, the difference between a hard margin and a soft margin. A hard margin requires 100% training accuracy, no mistakes allowed, 0. As you can guess, it's incredibly sensitive to noise and highly prone to overfitting. But a soft margin? It acts more like an experienced football coach who's totally willing to ignore one bad practice from a star player because they know it benefits the team overall. It intentionally allows a few classification errors just to create a much more stable, generalized boundary. So how do we actually control this flexibility? We use something called parameter C. Parameter C is our regularization parameter. Think of a large C like a super strict school principal who allows absolutely zero rule breaking.
It forces a really narrow margin to get every single training point perfectly correct. A small c is way more relaxed. It's like a laid-back teacher allowing a few imperfections, which yields a much wider margin that generally performs way better when we show it new, unseen data. But hang on, what if tweaking the strictness just isn't enough? What if a straight line literally cannot separate the data? Picture this. You're trying to draw a single, completely straight line through a playground to separate kids standing in a perfect circle around a central fountain. Because they're in a circle, a straight line is mathematically impossible. You just can't do it. That leads us right into Section 4, the kernel trick. Prepare yourself, because this is one of the most remarkable, mind-bending ideas in all of machine learning. If two crossing roads look like they intersect from the ground, you'd think cars would constantly crash, right? But if you look at those exact same roads from an airplane, you realize one is actually a bridge. They don't intersect at all in 3 dimensions. The kernel trick is exactly like that. It's a mathematical shortcut that allows SVM to behave as if our flat 2D data was suddenly lifted into 3D or even higher dimensions. Up there, a flat plane can easily slice right between the classes, and it does this without the massive computational nightmare physically moving all that data. We pull off this illusion using mathematical functions called kernels. You've got the linear kernel for your basic straight lines and the polynomial kernel for nice curved arcs. But the absolute rock star here is the radial basis function, or RBF kernel for short. The RBF kernel essentially acts like shining a spotlight down onto each observation. This lets us model highly complex overlapping patterns, like trying to use chaotic weather variables to predict a wildfire. It flexes the boundary to perfectly wrap around really complicated data shapes. Section 5. SVM in practice. Let's see this in action.
Now that we've built this incredible geometric foundation, let's talk about the Python workflow for solving real-world problems. The steps are pretty straightforward. We split our data, scale our features, fit the model, predict, and evaluate. But I really want to emphasize step 2 here, feature scaling. Since SVM is 100% reliant on physical distance and geometry to find that margin, scaling is absolutely non-negotiable. If you don't scale your data, a massive number like 50,000 acres burned will completely overshadow a super important but numerically small number like a 35-degree temperature.
And of course, once we make our predictions, we have to evaluate them. And general accuracy just doesn't cut it here. We use a confusion matrix to pinpoint exactly where we're making errors. Going back to our wildfire example, predicting a high-risk fire as low risk could quite literally be catastrophic. By breaking down the results in this table, we can calculate precision, recall, and F1 scores. This ensures we aren't just getting a decent overall grade, but that we absolutely aren't missing those critical high-risk wildfire events. Now, as amazing as SVM is, I have to be honest with you, it's not a silver bullet. Knowing when to use it is half the battle. If you need super simple, readable rules, stick to a decision tree. If you've got a massive tabular dataset with millions of rows, honestly, XGBoost or LightGBM are going to dominate. But SVM, it shines the absolute brightest on carefully prepared, moderate-sized datasets where the boundary between your classes is highly complex and nonlinear. That is its sweet spot. And because it's so incredibly good in that specific sweet spot, SVM remains a total powerhouse across almost every scientific field. In healthcare, it maps complex biomarkers to help diagnose diseases. In the financial sector, it sniffs out subtle overlapping patterns to catch bank fraud. Over in sports science, researchers are using it to predict an athlete's injury risk by combining metrics like jump height, knee angle, and hip strength. It is just a phenomenally robust, elegant tool to have in your kit. So, we've successfully mastered how SVM finds the perfect geometric boundary by leaning on support vectors and the absolute magic of the kernel trick. Thank you so much for joining me for this explainer. But before we go, I want to leave you with a little something to ponder until our next analysis. We just solved a massive classification problem using pure spatial geometry. But what happens when an algorithm decides to abandon geometry entirely and instead uses raw probability? How could an algorithm mathematically be considered naive, yet still manage to be one of the fastest and most effective text classifiers on the planet? Well, we're going to find out next time. Keep learning, and I'll see you then.